Hello, everyone. We are going to start section 4.1 here this evening. This is about exponential functions. So we'll kind of talk about what an exponential function is and how it works. So a function that models exponential growth, it's going to have values of a and b so that it has this sort of form. A is the starting value that you have. B is the growth factor per unit x. And so here the big idea is that x, the variable, is an exponent. So everything that you've seen up to now, usually when it came to the exponent, you actually knew what value it was. If you had like x to the third plus 5x squared plus 7x minus 2 or something, when we were doing polynomials, we knew what the powers were going into it. We had values for the powers, and what changed was the base of the power, what number was getting squared, what number was getting raised to the fourth, whatever it was. An exponential function kind of turns that whole notion on its head. And so here what we're doing is we have a fixed base, and then the power can change over time. This particular picture is showing us 2 to the x power and where it's coming from. If we make an XY table here, if we do 0, for instance, 2 to the 0 power, I'm sure you've encountered this little factoid before, but anything raised to the 0 power is going to equal the number 1. So then that gives us this point that they've plotted right there, which is 0, 1. If you put in 1, 2 to the first power is going to be the number 2. So you have 1 comma 2 right there, giving you that point. If you use 2 as the power, that gives you 2 squared, also known as 4. So you have that point, 2, 4. And you could keep on going, have the third power, which will be 2 to the third. 2 times 2 times 2 happens to be the number 8. And the numbers just keep doubling over and over and over again. And they're doubling because the scale factor, the growth factor, is a 2. That's the base of the power. Fun fact, if you have negative numbers, it's possible to have negative numbers as an exponent as well. If you have 2 to the negative first, that's the reciprocal, which is 1 over 2. So that's why we're getting this value right here. If you do negative 2, 2 to the negative 2 power is going to give you the reciprocal of 2 squared. So the negative means do the reciprocal, and then you do the reciprocal of 2 squared, which is 1 over 4. That's giving us this value. And then if you do that again here, you're going to get negative 8. And the thing to notice is that it actually flattens out at 0. So it has a vertical asymptote like we've seen. Or actually, I'm sorry, that's a horizontal asymptote, excuse me. It has a horizontal asymptote. It levels off at 0. And so this is an example of an exponential function. One thing I will mention of why this is a thing and why anybody cares and like why this is a big deal. Exponential functions where they have like a starting amount and a growth factor. One kind of scenario that this kind of branch of mathematics is applied to would be things like virology and epidemiology. So things related to, I don't know, a really nasty virus that spreads like really fast. And that's this kind of the shape of this graph is why that's a big deal and why it's kind of a cause for concern, because it starts out relatively flat and then it just reaches this point where it just starts getting higher and higher and higher, and then it just shoots up into the stratosphere here, and it just keeps getting higher and higher, growing faster and faster. And so I've been teaching this topic for a number of years, and I've always used this example because you know, epidemiology has been around for a while, but here lately, I think a lot of us, for better or for worse, have gotten a very vivid picture in our mind of what these kind of graphs are describing and why they're a big deal. So in case you wonder like what any of this stuff is for, that's a prime example of a field in science and medicine where these kind of functions are a topic of interest, let's just say. So let's look at some examples here. So they say at the beginning of this section, we learned that the population of India is 1.25 billion in the year 2013. It has an annual growth rate of 1.2%. It's represented by that growth function. So they go ahead and give us the growth function, where T is the number of years since 2013. To the nearest thousand, what will the population be in 2031? So maybe you read news stories about these kind of things. I know I've certainly encountered them from time to time, but this is the kind of thing where they use an exponential function to make a prediction. So our goal is we want to find out what it is in 2031, bearing in mind that our starting point is 2013. So you do not want to put 2031 into the function for t, because that's not going to give you the right value. If we do 2031 and subtract 2013, that is going to give us the number 18. So that basically means it's 18 years from now, or rather 18 years from 2013. Actually 9 years from now, which is kind of freaky to think about. But anyway, so what this will be, we're going to do P of 18. And that's going to be 1.25 times 1.012 raised to the 18th power. So let us grab ourselves our friendly neighborhood calculator, and you have to remember your order of operations. Exponents come first, then multiplying. So if you do 1.012 and raise it to the 18th power, you will get this number. They say to the nearest thousandth, which is 3 decimal places. So we'll maybe go one more than that. That's going to be 1.2395 is what that is. And then if you multiply that by 1.25, that's going to give you 1.549 if you round that off. And fun fact, they do tell us it's starting at 1.25 billion. So then by 2031, India can expect to have 1.549 billion people. So don't just say the answer is 1.549, it's 1.549 billion. That's like the units that we're operating with here. So there you go. That's kind of what you could expect the population to be in 9 years' time. And 9 years have already gone by. So we're like halfway there. Let's see. We're halfway there. Whoa! Anyway, it had to be done. I'm sorry. All right. Another thing that this is used for is money. So this is a little something known as compounding interest. And what this fancy looking formula will do for you is it can tell you how much money you would have in a savings account as they keep calculating interest, like month after month, or maybe, I don't know, day after day. Sometimes they do it like every 6 months. It kind of depends on the account. This is also, by the way, how loans work and also credit cards. So if you if you have a loan for a certain amount, or you have a credit card balance for a certain amount, and if you don't add any additional money to it, you just have only the interest, it also works with that too. So how does compound interest work? So A of T is the account values. That's basically the amount that you have at the end of all this, which is what you would usually want to know. You have the time that goes by, which is T. That's going to be in years. P is called the principal, which is basically financial speak for the starting amount of money that you have. You also sometimes see the term present value, which is how much you have now versus how much you'll have in the future. R is the annual percentage rate, the APR. You want to have that expressed as a decimal. So you're going to want to change the percent to a decimal. And we'll get into how you do that in a little bit, but just know that that's what R is. It's the rate that they quote you. And then there's N, which is the number of compounding periods in 1 year. Usually you'll have like monthly, which would have an N of 12 because there's 12 months. You might have like quarterly, where they do it 4 times a year, once every quarter. Sometimes you could have it like where it's daily, where you'd use the number 365 for the number of days in a year. It just kind of depends on the problem. Quarterly and monthly are the most common ones you tend to see, but I mean, they could do it however often they feel like if they wanted to. So let's look at this example here. If we invest $3,000 in an investment account paying 3% interest compounded quarterly, how much will the account be worth in 10 years? So let's break down what they tell us, shall we? The starting money is the value of P. So we know that P is 3,000. We know the number of years that go by, that is T. So T is going to equal the number 10. They tell us that it is compounded quarterly. And again, there are 4 quarters in a year. There's 4 quarters in everything that you split into quarters, because that's how quarters work. They're a fourth of something. So quarterly just means that the N is going to equal 4. And then we've got this right here, which is the rate, the interest rate. So what we need to do is take 3% and make it a decimal. And the way to do that is if you do percent and divide it by 100, that will change it to the decimal form. And again, you can do this with a calculator, that's fine. I don't judge. 3 divided by 100 will give you 0.03. Fun fact, it is not 0.3 because 0.3 is actually the same as 30. 0.3 is actually 0.30, which is 30%. So it is not 0.3. If you are trying to do this and figure it out in your head, just know 0.3 is 30%, not 3%. Again, if you just divide it by 100, the calculator will figure it out, and don't worry about it. But all right, let's do this here, shall we? So we have A is the final amount that we want. And we're going to have P times 1 plus R over N raised to the power N times T. So that's, well, let's write it down first and then we'll put in numbers. So what do we have? We have 3,000, and then parentheses 1 plus, what is that? 0.03 divided by 4. And then we're going to raise that to the power of 4 times 10. So what we can do, I think it's a good idea to work out the power because that's usually not super bad. 4 times 10 is going to be the number 40. And then a lot of this, we can just figure out using like a graphing calculator. It can do a lot of the heavy lifting for us. So let me show you here what we've got. So we started with $3,000. So we're going to just type 3,000. Go ahead and do the parentheses just the way it's written. It is 1 plus 0.03 divided by 4. And you close the parentheses, so it's going to look a little something like that. 3,000 times in parentheses 1 plus 0.03 divided by 4. And then what we need to do is just raise that to a power, which I figured out earlier happens to be 40. So there's the 40 you can see there. And if you push enter, that'll give you this amount right there. And this is money, so you're only going to round to 2 decimal places. It always perplexes me when I give money problems and then I have students who give me like 8 decimal points or something ridiculous like that. And I'm kind of like, have you not used money before? Like, anyway. So what is that? That's 4,045.05 if you round it off. So 0.045, we'll round that off to 5 cents. Let's go back to what we were doing. So when all is said and done, that tells us that the amount we will have is $4,045.05. So there you have it. Okay, there you go. Okay. Let's see what else we have going on here. An initial investment of $100,000 at 12% interest is compounded weekly, and they say use 52 weeks in a year. What will the investment be worth in 30 years? Okay. Well, that means that our starting value is P, that's 100,000. R, we're going to do 12% divided by 100, which for those keeping track is going to be 0.12. There are 52 weeks in a year. We're doing it every week. So that means N is equal to the number 52. And then we're doing this for the long haul. We've got 30 years, which is the time that goes by. That's going to be 30. So let's see what this will look like. So A is going to equal P times 1 plus R divided by N, all raised to the N times T power. I've been doing this a while, so I know this formula by heart. You can use notes on the test, so by all means, have the formula written down somewhere, and it's perfectly fine with me if you look it up. What's important to me is that you know how to use it. Let's see. So what is this? We have 100,000. We've got 1 plus 0.12 divided by 52. And then we're going to raise that to the power of 52 times 30. Let's find out what 52 times 30 is. That is 1560. That is a big number. So 1 plus 0.12 over 52. And we're going to raise that to the power 1560. And again, let us get our friendly neighborhood calculator. And we will say, oh, great and powerful calculator, we humble mortals beseech thee, bestow upon us a gift of thy wisdom, and tell us, please, what is this going to be? So let's go ahead and show you what we've got so far here. So you've got 100,000 and then parentheses 1 plus 0.12. Divide that by 52 because we're doing it by 52 weeks. And then we're going to raise that to the power And it's that number I have right there, 1560 was the number I calculated for the power right there. There it is. And you push enter and holy moly, that's an awful lot of money. All right, so that number, which is over $3.5 million. That's a lot of money. That's also over 30 years, so that it takes a while. But anyway, let's see here. And good luck nowadays getting an interest rate of like 12% from a bank. That's you're lucky if you'll get like 1.5% these days. But anyway, what is this? This is 3644. Then what? 675.88. Don't forget about the 88 cents. All right, there you go. $3,644,675.88. There you go. That's a lot of money. Okay. Let's see. What else do we have going on here? So there is a number known as E. The number E gets its name from a Swiss mathematician named Leonhard. It's actually pronounced Euler. It kind of looks like Euler, but it's actually pronounced Euler. And so they named it in his honor, E. And it is this number right here, 2.718281828. And it's a number that's sort of like pi. It's this kind of funky decimal number that's roughly 3 that shows up in different kinds of situations related to exponential growth. The definition of E, where it comes from, is we just did the problem where we did the rate divided by 52 and then raised it to a really huge power. Well, fun fact, you've got this kind of push and pull going on where if the number gets bigger, when you divide, it's making things smaller, but then when you do the power, it's making things bigger. And so you've got this kind of push and pull in opposite directions here. And it turns out that eventually they sort of balance out and sort of cancel each other out. And if you make the value of n big enough, then you're going to get a number that's roughly 2.7, specifically E 2.718281828. So it's this kind of funky, wacky decimal here. So they say use a calculator to find E to the negative 0.5 and round to 5 decimal places. When you do questions like this on your exam, this should be a one where like everyone gets this right. Like all you need to know is how to do this in the calculator, and like there's no reason any one of you should get this question wrong. So where do you find E? That would be helpful to know. So if you look on this graphing calculator here, this is the TI-84, you will see there's a button right here that says ln, and then directly above it, you see E to the X power. So usually when you do E, you're doing it to like a power of some kind. And even if you don't have this specific type of calculator, any like scientific or graphing calculator will usually have E grouped together with an ln key. So what you would do, because it's in blue, I'm going to do the second key and then push the ln key, and you will see that gives me E, and then it's got a power there for me. So I can type in a power that I want for E. In this case, it's negative 0.5 is the power that they asked me to do. So I'll just type in negative 0.5 while I'm up there in exponent land. And if I press enter, I get, they wanted 5 decimal places. So it's 0.60653. So that is the answer. So let's go back to our thing here. So again, this is, if you're using a TI-83 or a TI-84, you do second and then you do the LN key. And if you do e to the negative 0.5 power, that is approximately 0.60653. So again, know how to do that with the specific piece of technology that you're using. And again, these kind of questions, like on your exam, like everyone should get these right. Like there's no reason why, like this is as like easy as it can get. You just type something in a calculator and see what it gives you. But there you go. That's e to the negative 0.5 power. All right, and then we've got continuous growth and decay. So fun fact, we were looking at banks, and banks will operate according to very regular and well-behaved schedules. Like they're going to accrue interest once a month, or they'll calculate your balance every day or every 6 months or whatever. But fun fact, things in the real world, like, I don't know, viruses or bacteria, or I don't know, the population of fish in a lake, whatever it is, those kind of things do not behave according to nice and neat regular schedules. So they grow continuously, and so they use the continuous growth and decay for those kind of situations from the sciences. If you're wondering where something would decay, that would be something like radioactivity. So, so like something like carbon-14, for instance, you might have heard of carbon-14 dating, where like archaeologists can take like a bone or a piece of pottery or something, and they take something that's got some organic matter left behind in it, and what they can do is that based on the radioactive decay of carbon-14, which is this isotope in lots of living things, it's very, very small traces of radioactivity, and it takes it like 5,000 years or something ridiculous like that for half of it to go away. And so radioactive decay is something where like you have a bunch of it all at once, and then as time goes on, as time passes, the radioactivity dissipates, and then after a while, it's no longer a danger, for instance. So here they're just saying that if R is less than 0, then the formula is going to be decay. And if R is bigger than 0, it's going to represent growth. So you've got a starting number A times E, and then you do the rate times the time that goes by. All right. So first we have a money example, and then we have a radon radioactive decay here. But so a person invests at a nominal 12% interest rate, and it's compounded continuously. Most real world banks are not really going to do this, but we're just going to sort of imagine that we can grow, we can have our money grow continuously. So what do we have? We're going to have A equals little a times E times R times T. So little a, the starting amount is 100,000. That's how much you have to begin with. The rate is 12%. And like before, divide the rate by 100 to make it a decimal, 0.12. And then the T is the time, the years that go by. So in this case, T is 30. So we have A equals 100,000 E, and then we're going to raise that to the power of 0.12 times 30. 0.12 times 30 is, that should be 3.6. Yeah, it is 3.6. All right, so we've got E to the 3.6. And then if we get ourselves a friendly neighborhood calculator here. So I'll get mine here. So we've got 100,000 to start with, 100,000, there it is. And then we're gonna do seconds, and then the ln key, which is over here. There's the ln key, second ln gives you e to a power, and the power we wanted was 3.6. So we're gonna do 100,000 times e raised to the 3.6 power. And if we do that, we get 3, 6, 5, 9, 8, 2, 3, 44. So we get a huge number that's actually pretty close to what we had in the other example. This is 3, 6, 5, 9, 8, 2, 3.44. Don't short them that 44 cents. You're gonna need that 44 cents, y'all. All right, so it's about $3.6 million. If we go back to the other example that we had how much? That's also 3.6 million roughly. There it's like 44. Here it's like 59. So what you'll notice is that it does make a difference by compounding more frequently. It does have an impact, and it does boost your yield ever so slightly if you keep compounding it on a continuous basis, like every second of every day of every year, over and over again. Radon 222 decays at a continuous rate of 17.3% per day. How much will 100 milligrams of radon decay in 3 days? Notice that they do give us a rate per day. Up to now, we've been doing everything in terms of like years, but in this situation, we now are talking about actually a daily rate, which is fine as long as these are consistent. I mean, you could do it by month, you could do it by day, or you could do it by year. You could do it by century if you really felt like it. They just need to be measured in a consistent way. So this is just telling us that T equals 3. The rate is going to be 17.3% divided by 100, which is going to be the number 0.173. And then the starting amount that we begin with is 100, because we have 100 milligrams. Since this is decay, that means when it's decay, you need a negative value of R. That's an important detail about this problem. When you have radioactive decay, when you have some sort of exponential decay, it's going to have a negative value of R. So we're going to have 10, we're going to, or I'm sorry, not 10, 100. We're going to multiply that by E and then raise it to the power 0.173 times 3 days. Let's find out what 0.173 times 3 is. That is 0.5, or I need to make it negative, excuse me. I just harped on that, but then I neglected to do it myself. So what is that? That's 100 E, and then negative 0.173 times 3 is negative 0.519. And let's get our calculator here. So we start with 100. There it is. You do second, and then the ln key, which lives right there. You're going to have e to a power, and the power in question is negative 0.519, which we found earlier. And if you work that out, it's going to be 59.51 is what that is. They don't tell us how much to round to, so we'll just give them 2 decimal places here. It's going to be 59.51 milligrams. So there you have it. That is how much radon 222 there will be left. There will be after 3 days. So that's an example of radioactive decay. All right, so that is the end of that section. So then we will start the next section here in just a minute here. Let's go ahead and stop the video.